Sumit, visible hai?
Yes, sir. Yes.
Okay, so we were discussing about the basics elements of geodesy, and in that we have started with looking with the how the development of this shape of Earth has taken place. So initially, people have started talking about the sphere, then the evolution up to ellipsoid taken place. And when the ellipsoid has been decided that okay, our Earth is something ellipsoid, which is pressed from poles and elongated at equator, we gradually move towards finding the mathematical surface. So, see, the idea of this geometrical geodesy, where we are talking about some uh, statistics or some kind of mechanism or principle by which we could use this model, the ellipsoid model, for measurement purpose. That's what the term is geometric means. Whenever we can measure something from anything, that's why we are studying that part of geodesy where we are using it for our measurement purpose. So that's why it is called as geometric geodesy. So in geometric geodesy, we are looking for first solution is that how our Earth look like. So from terrestrial point of view, we are just in that manner we are identifying that whether our Earth is a sphere or ellipsoid. So obviously it is ellipsoid, but mathematically it was proven uh, how this concept of ellipsoid taken place. So that was explained. Now, once it is decided, you define the mathematical values, which is semi-major axis, semi-minor axis, flattening, eccentricity. So that's how you define your Earth. Now your Earth is defined. Now what you want is that you want to develop the understanding for or of a concept called global navigation satellite system. So now when it is clear to you that your Earth is ellipsoid, now how you can define the points on the surface of Earth for a different continent altogether. So suppose you are in India, somebody is in US, how it would be a different value. So in order to do so, that means for getting a unique value for a particular region. So let's say if you are in sitting in Madras, or maybe you are sitting in somewhere in Bangalore, you would be getting a unique value for your region. It should not be contradicted with the values which somebody is getting in US or somebody is getting in Australia. So the initial concept of having this unique value started from this understanding that we should define the coordinate system first. So if we are able to define the coordinate system, then this problem would be solved. That people will not get the values which are contradicted in nature. Means the value would be unique. Okay, and in in this particular instance, this the concept of Earth center and Earth fixed was you know, explained or conceptualized. So obviously, this coordinate on the so-called ellipsoidal Earth was considered to be latitude, longitude, and height. We have explained this. You are expected that you should draw this figure on your note sheet and practice it, so that this whenever somebody questions you during any interview, how do you define the latitude, longitude, and Earth? Longitude and the on the surface for any point on the surface of Earth. So you would not be deviated from any type of misleading answers. You just have to be very crystal clear how this geodetic latitude, longitude, and height would be defined from an ellipsoidal Earth. Then this Earth-centered, Earth-fixed. So this Earth-centered and Earth-fixed concept is conceptualized to get the coordinates unique at a particular place, and this is the fundamental coordinate system required for the global navigation satellite system, or in your case the GPS, for defining the position on Earth in Cartesian system. So in the previous, it was the latitude, longitude, height, which is also called as ellipsoidal coordinates. Okay, but or geodetic coordinates. But here you are defining the coordinates as x, y, z. Okay, in x, what is x, what is y, what is z is it is discussed. So we are not going to discuss it again. So it quickly move on to coordinate system transformation. That is your lab one, which I think you already have started working on it. Then this topocentric system or a datum, that means sometimes what happened, people who are having this global coordinates understanding, they are little poor in terms of local implementation. So what people thought that, okay, we should have a topocentric system also. Topocentric means you define your origin on the surface of Earth, and you'll have a relatively understandable coordinate system, which is having northing, easting, and up component. And this northing, easting, and up is generally expected that you would work on with the help of the projection system which you have. So what people thought that, okay, if you have a same point in xyz, how do you convert it? So this conversion is taking place in the realignment of this axis according to the xyz of the ECA. So this requires the translation, reflection, or and rotation. So this the after this translation, reflection, and rotation, it is expected that this shift would take place, and then you will transform the coordinate in from XYZ to NEU for your local working. So this is very much clear from conceptual point of view. Similarly, we move ahead with understanding little about the datum when I say the height system. So in order to discuss the height, first we need to study about the gravity. So that's the one point which all of you should understand, that your gravity varies from place to place as the mass distribution is not the same. And as the mass distribution varies, that's how your gravity varies. And the height system also need a little introduction. So this gravitational potential concept applied with this so-called for a rotating ellipsoid, which is having some rotation term, oblateness term. Somebody's mic is on. Okay, so we discuss this, then we arrive at this so-called the, the mathematical surface, the four parameters that are needed, which is major axis, GM, J2, and omega. So these are the values based on which ellipsoid is defined. Then this variation from the geoid and topography, we already have explained this multiple times, so no need to revise it again. It is the actual height, I mean the ellipsoidal height and the orthometric height. So your local work cannot be done in ellipsoidal height, it has to be orthometric height. So conversion, I have explained it in last class, that there are various models available. One such model for applying the geoidal undulation on your study area is EGM08. And when you have this EGM08, that means you know the undulation information above ellipsoid. So when you remove it, above undulations above this so-called ellipsoid, you get the a particular orthometric height. So this is the geoid, which is so-called geoidal height, which is with respect to WG64. Okay, so this is the equation. This capital H is nothing but H minus N, the relationship. Please remember always that this orthometric height is height which is from the mean sea level, and this capital small h is the height from the ellipsoid. So both are the two different heights. If you drop a plumb bob from a point, that will follow the so-called gravity line, and it is a curved in nature. So inside Earth, it would be curved and goes to the center of mass of Earth. But the ellipsoidal is a perfectly mathematical surface. If you drop a normal, it would not go to the so-called center of mass of Earth. It would be a perpendicular from that point and hit on the equator somewhere. So that's a two different thing. Difference between this ellipsoidal line, or you call it ellipsoidal perpendicular, and this geoidal perpendicular, that would be called as the deflection of the vertical. So that means the direction of ellipsoidal normal and the plumb line at a given point is called as deflection of vertical. The transformation from ellipsoidal height to orthometric height requires to know the local geoid height that we usually do, and this geoid height is given by various satellite missions which are available. And one such mission is ECM-08, that means 2008 model of the uh, European geoid model, which is popularly used, but the recent updates are also available for that particular. Then this world geodetic system, which we discussed, how this is used. So what are the important point is you remember this, what is Z, what is X, what is Y, and how it is defined. So please remember, as I've told you, your Earth is not a static body. Yeah, it is moving, it is revolving, it is rotating. So your Z cannot remain same at the same time. You cannot have a same Z every time. I'll show you one video today, so that will open up your mind a little bit, so that you could understand several concepts related to this this satellite geodesy, which are very much required for defining your so-called perfect coordinate system required for such uh, technology, which we call it as GNSS. Please remember, GNSS is a technique where your satellites are in this space. Okay, it is not on the ground. So what we are feeling on the ground, it's perfectly different from what satellites are facing on the space. So in order to work in that technology, you need to understand several mechanisms before we finally reach to the points. So it is not a cakewalk. I mean, it has been made a cakewalk, but it's very complicated. But at the same time, it is very understandable also. So you need to also understand that your Earth is not a homogeneous body. It is perfectly heterogeneous. It has solid, ocean, atmosphere that constitutes the Earth, and then your z-axis, which is the direction which we think that it is coinciding with the Earth rotation axis. Eventually, it is not. Your Earth rotation axis is deviating per day, per year, every time. So, in order to define, whenever we define a coordinate system, okay, so we cannot define it for any instantaneous moment. We cannot define right now, isn't it? Because if we define it right now, tomorrow it will be different. So by convention, people or the scientists, they have defined this x, y, and z axis of the so-called the for a particular coordinate system. They defined at a particular epoch, and conventionally they have defined. Okay, there is a difference between the conventions. What conventions you are following? So this z-axis, which is defined as direction of conventional terrestrial pole at epoch 1984 as defined by BIH. Then the x-axis is coincident with the zero meridian, which is also known as the intersection of the equator with the Greenwich meridian, and the line joining that intersection point would reflect as zero meridian, but at epoch 1984. And y-axis would make right-handed coordinate system, the ECF, orthogonal geocentric coordinate system, and is defined using satellite Doppler coordinates, and it is up to 1 to 2 meter accuracy. This this is the world geodetic system they have defined with the involvement of multiple countries in the so-called global navigation satellite system. It is not accepted that you all countries would accept the world geodetic system of United States. So what they have thought, okay, they arrived at one conclusion, is that why cannot we establish our own stations around the globe and then we define our own frame. So this International Terrestrial Reference Frame (ITRF) is defined by an international body which is called as IERS, and this IERS full form is International Earth Rotation Service, which define this ITRF. And this ITRF is same as WZ4, but both are different in the sense that WZ4 is maintained by US Department of Defense and has their a mechanism where they use the GPS station as the control points. But in the ITRF, they have the VLBI stations. They are co-located with SLR, co-located with GPS. So that's how they find it. Quickly, we'll go back to those particular conditions, how the ITRF is different from your so-called world geodetic system. But anyways, you should know that WCT4 from US Department of Defense, and it is a reference frame. Please remember, it is a reference frame. Reference frame means it is a ellipsoid. It is not a coordinate system. It is a reference ellipsoid. Okay. Similarly, ITRF is also a reference ellipsoid. So the difference between regional and reference ellipsoid is we have explained that every country and every territory has its own. We have several examples: Clark, Bessel, Everest, now GRS 80, now converted to WS84. So we all have, and we can convert from one to another. Now, obviously, the vertical datum, which we explained, is that, in fact, I've shared one paper also to discuss about the potential, the geopotential, as well as the MSL, how it varies. Okay, and in fact, that's the reason why people are now looking towards the satellite missions or airborne mission to fix the gravity in particular region. Okay, satellite altimetry for surface, sea surface topography, altitude level. Now, this was the end of the previous discussion, which we have concluded is that is a datum or coordinate system sufficient in practice? That's what our question. So, I mean, people thought that okay, while defining a coordinate system or reference system would serve the purpose. Answer is no. What we need to do, we need to access it physically. So whatever conventions we are doing it, whatever thought process we have behind the defining the coordinate system, we need to realize it also. So in order to realize it, what we need to do, we need to think of a process how to define it physically. So that's how we arrive at a frame. So need for reference station whose coordinates are well defined in a coordinate system. That's the control points I'm talking about. So need for reference stations. So those station constitutes the frame. Example of WS84. How do GPS users tie their measurement to WS84? Most datums are accessible through station coordinates from old surveys. GPS can be more precise to those points. Obviously, those points have been defined way back, let's say 1970. And if you again revisit those points and you convert, you will never get this local coordinate anymore the same because that point has shifted because your whole continent inside the tectonic movement is happening and this point is shifted gradually. How much shift is there? At present, it is considered as something around 50 per year. So it means 5 centimeter per year. Every point is shifting. So that means the point which you are establishing today will have a shift of 5 centimeter. No, after the year. So that means after let's say 10 or 15 years, you'll having a shift of about 100 meter. So your station cannot be at the same position. So that's the question which we need to understand. So problem, datums are typically static. When we consider datum, when we define datum, we consider that there are no dynamics in it. But eventually they actually move and deform. And generally it is, I mean, it has been practiced to define this global datum or a continent-wide datum, and they cannot be perfect as they rely on imperfect models and measurement. If you define a datum on GPS measurement, that measurement is itself is changing. So your datum cannot be perfect, but we have to define it just to make sure that we are able to do our work. Okay, it should not be that our work should be stopped. We have to do the work also. In fact, for the same manner, you could see that the the benchmarks, the Survey of India benchmark were established in late 80s, but still they are being used. In fact, if yesterday I went on a field visit where India's largest solar plant is being established near Prayagraj, we have to do the survey, but that survey is being conducted, and that is to be done by with the same MSL which we have established in 80s. So that doesn't mean that we'll stop the work. Obviously we understand the deformation, understand the process how it is deforming, but we have to do the work. Okay, so with this I think we'll stop here and we'll share the next slide. Let me just again open it up. So we were discussing previously the part one. This is the part two of elements of geodesy. Okay, in this we will discuss about the Earth rotations, time system, conventional systems and frames, tides and loadings, etc. So the objective of part one is to introduce you with the terrestrial coordinate system. Okay, here we will introduce you to the Earth rotation and eventually the inertial system. That means when you move yourself from this Earth surface to the space, just move out of Earth and you see how your Earth is moving in the space. Is it static in nature or it is rotating? If it is rotating, what are the effects on the Earth's surface from other planets? We need to understand that part. Okay, so this is your Earth in the space. This Earth, which is part of the solar system, you have Sun, you have Moon, you have other planets. Okay, you. So this is this is where we belong. This is the Milky Way Galaxy, isn't it? So you just see this beautiful. Sumit, my cursor is visible.
Yes, sir.
Okay, so this is the Milky Way Galaxy, and this is zoomed up to see that this is Sun, this is Moon, this is Earth, this is Moon. Then there's the other local cluster, the local group, the local supercluster, the universe. Okay, so I mean, this, if you just zoom out of your point to look at this space, it's different. It's altogether different. So in order to discuss that, we just need to first look for you know few points before we move into the details. Why should we care? Okay, why should we care about the Earth in the space? The stars have long been essential to positioning and navigation. So those who are a little more curious, they must have seen that in the previous era, people used to sail with the help of a star throughout this throughout on the sea. They use those star for marking their path. So the relation between human and stars have been long. Okay, it is not just a few years of history. It's a very long. People have used the stars for positioning them. as if the stars are static to them, and it is continuously day by day they are looking at the same star once again. So they thought that, okay, why not to use those stars to measure our positions? Okay, so stars have long been essential to positioning and navigations, and the basic physics which is involved. So Newton's law are valid in the inertial frame, as we all know. No force due to the motion of the frame itself. A counterexample is the fictitious or non-inertial centrifugal force. See to the right. So what is the Newton's second law? It is in inertial frame you define F as a ma. Okay, the force is equal to mass into acceleration. Then this obviously this the if it refers to classical mechanics, so d by dt of the from inertial frame to rotating frame at a uniform speed, we define this equation like this. Okay, this position becomes, if you introduce this r, so dr by dt. If you introduce velocity, the velocity would be also introduced. So this Newton's second law in rotating frame, it means force applied in inertial frame minus this Coriolis force and the centrifugal force that is resultant with the your so-called MA. That constitutes this MA. Okay. So this basic physics, we will start with understanding, okay, when a body is rotating, how the effects would be would look into it, what type of resultant force, how this resultant force would look like in a rotating frame. Okay, see, this is what we see when we look at the space fixed versus earth fixed reference frame. So there are two things when you go into the space. Okay, so I've told you in you have seen one video in the last previous classes that when you look at the satellite which is moving around the earth, it looks like that there is a perfect orbit, and this perfect orbit in which a satellite is moving, there is no problem at all. If it is geostationary, it will follow the earth rotation. If it is non-geostationary, it is in a sun synchronous system, then it will follow the particular orbit to maintain it. So this the left hand figure, which is called as GPS orbit, that is the figure when you consider the inertial frame. That means you are not on the surface of earth, you are outside the earth, and in the space you are looking at the orbits, how this orbits looks like. And we have seen the thousands of satellites are in this space, isn't it? So that's how you see, if you observe any one satellite, you will see the path of that individual satellite. Similarly, what will happen if you see the same satellite from your so-called earth surface? If you are not in the space, you are on the surface of earth, just like we are now standing on or sitting on the earth surface. You just see above, you see no satellite, but if you observe the path, it would not it will not be the same as the left one, it would be a different one. How it would be? You see the right figure. So this is the classical example of understanding what is the difference between space fixed and earth fixed. So when you are on the earth and you fix the earth, so obviously to maintain that the same harmony, you have to shift the path. Okay. So somebody would say, how do we understand that why the both two are same? So just simple. If you are on the space, you would look at earth as rotating and the satellite is moving in the orbit. Okay, so at a particular instant the satellite is following at a particular or over and above a particular region. Okay, that's true. But in the case of earth fixed, it will not be the same. You have just fixed the earth, because that's the earth's fixed frame, it is not rotating anymore. Okay, it is fixed. The moment it is fixed, so what satellite has to do? Satellite has to travel to those areas to make sure that those particular region would be covered. So that's why the path is shifted, or I mean this sky plot is changed drastically. So these are the two frames. Let me just show you one video of satellite path in the space. There's one very good video. I'm just looking at it. I'm sharing the tab for just a moment. Let me see if it is visible or not. Is it visible?
Yes, sir.
You see what we are trying to present it here. On the right figure, you first look. On the right figure, you are looking at your Earth as a moving body. It's just rotating. Okay. You see India now here. This is your India, and that's how satellite moves. Same path you see on the left hand side, which is Earth fixed. That Earth is not rotating. Okay. So at different epoch, so at different epoch at the bottom it is epoch. Here it is epoch at the bottom, which you can visualize. I'm just doing it away. For the same moment, the same epoch, the two different frames. One is Earth fixed, another is space fixed. So when I say you move out from Earth and go into the space, I want you to look at such Earth that is presented on the right hand side. It's very decently, it is rotating. But whenever you are on Earth fixed, you do not move. You do not consider yourself to be rotating. You just look at how amazingly this plot is being done. So that's the difference between the two. Okay. So this is the two basic difference between your space fixed versus Earth fixed reference frame. Why do we need it? Isn't it? This is the question. Every time you read something, you should ask yourself, why do you need it? Why there is a need to study space fixed and Earth fixed? Because please remember, we are studying the technology called GNSS or GPS, Global Navigation Satellite System, Global Positioning System. So satellites are very far from each other, far from our Earth. It's 20,000 kilometer away, 20,183 kilometer away, to be very precise, from the surface of Earth. Okay. There, in this space, there is a lot more forces acting over the orbit. We are relying on our satellite only to get a position on anywhere on the surface of Earth, which we consider as a very simple job. Whenever somebody says, you say, I have a GPS in my mobile phone, I can do anything. Okay. But that's not easy. I mean, you need to understand that part also. Second point is, we consider those satellites in the orbits as a control point, as a moving control point that help us in fixing my location on the surface of Earth. Just like I've asked you, what is the difference between defining a point and fixing a point? You told me that by defining means we need to define the point by giving an appropriate latitude, longitude, and height. When I say, how do you fix a point? So you say we need to take the measurement, the distance measurement from the fixed location around that point, and we take the length measurement or a distance measurement or angular measurement to that point, and that's how we define that point, just by taking sufficient number of the distance observation. Similarly, in the GPS, you take the space resection principle. That means you are taking the ranges measurement from those satellites in the space with the receiver in your hand. You try to make those connection with those satellites to fix your location, and when you fix it, you will get the latitude, longitude, and height. Okay, so this process of getting the signal from them without having any hindrances, it's not easy. We need to convert from several system to come back to in our earth centered and earth fixed system, because orbit is moving. You cannot apply earth fixed coordinate system to orbital system. You cannot fix the space fixed system to orbital system. So it's a three-way communication, three-way steps that we need to come down. First, we need to define the coordinate of the satellite in its orbit itself. Then this orbits will be converted to space fixed. Then this space fixed will be converted to earth fixed. If you do not know the coordinates of the satellite, you cannot work in GPS or you do not work in GNSS. This whole concept is failed. To work in this concept, the essential thing, the most important thing is you know the coordinate of the satellite in earth-centered, earth-fixed system, because you also want your coordinate in the same earth-centered and earth-fixed system. If you know this, then only your concept or this technology work. Okay. By the way, this all measurement, range measurement, coordinates. This is the job of the receiver. You simply get the output. That's the black box which you are seeing output as XYZ or latitude, longitude, height on NEU. But in the back box, this is how it is working. You get the coordinate of the satellite in ECF, you get the distance measurement, you solve the equations, and then you get the so-called, you adjust it. At the same time, you process the least square adjustment in the backbone, and then you will get the least square adjusted values of a particular point. Anyways, that is the you need why there is a need of studying this space fix, because you need to apply so much corrections to your data set. Then after that you will get this value. But anyways, nowadays you get simply the values, and if you are more into the application domain, you do not need to know how and where these different the the space fixed and earth fixed vector system are working. But otherwise people will simply call you as you know, a mere geographical person, or how do they call you as a geoinformatics professional if you do not know the basics of working of the GPS. Okay. Okay, coming back to this space fixed coordinate system. So please remember, we have studied earth fixed coordinate system, that is for the terrestrial purpose. This space fixed coordinate system is required so that you could define the coordinate of the satellite in this frame. Please remember, this space fixed coordinate system is defined for the so-called observation or location of the stars in the sphere. This is so-called the celestial sphere. If you are looking at a star right now, let's say if you just imagine you are looking at the star, how do you define the point? How do you define its location? Its location is so complicated if you define it directly in earth-centered, earth-fixed system, because your earth-centered and earth-fixed system will only observe that single star at that time. But you do not have any mechanism to measure that particular star. You need to first go back into the space, think how your earth is moving, because for that star, your earth is a moving body. Okay. If it is a moving body, the moment you are looking at the star and the moment you are taking the observation to the star, your position is shifted little bit from west to east. So it is not an easy task to define the coordinate directly in the earth fixed system. You need to first understand how the space fixed system look like. So this coordinate system, which is different from Earth fixed system, has its origin at the Earth center of mass. Please remember, it's very simple. No need to get confused. It's only two different system we are talking. Previously, we have discussed about the Earth centered, Earth fixed system. Now we are talking about the space fixed system. We are putting everything at rest in the space. This coordinate system has origin at same at the Earth center of mass, just like previous one, but the pole are little different. The pole is a celestial ephemeris pole, which is CEP. That is, Earth rotation axis coincides with CEP, which is called as also known as angular momentum axis. So you see here, this is your Z, this is your Earth. Now this figure would be much better if you put a Earth here, because Earth in your space is just a single small body. When you move yourself into the space, your Earth is a very small body compared to other planets. That's why it is represented by a point. Otherwise, if you put a bigger picture or a bigger body of Earth, this is the rotation axis of Earth that coincides with the CEP, which is celestial ephemeris pole. What do you mean by celestial ephemeris? Ephemeris is a term which is a Latin term, is given for the orbital understanding, or the so-called the parameter of the particular stars in the space. We represented the how to define a particular star in the space. We call it what is the ephemeris of that star. So this ephemeris term is a Latin term. But what is more important is the what do you mean by celestial? So celestial is a term which is defined to or used as an opposite to terrestrial. So what would be the opposite to terrestrial? It would be celestial. So the celestial is a body or a sphere, celestial sphere, where on its surface the star are plugged. So just like a huge balloon you are seeing, in that balloon from inside, if you observe, this whole sphere has stars stuck to it. That's how you look at it. And in between, you have your Earth. So this celestial sphere is celestial ephemeris pole is containing the Earth rotation axis, which is also known as the Earth angular momentum axis. Two fundamental planes are there. One is called as celestial equator, and another is called as ecliptic equator. Now, what do you mean by ecliptic? What do you mean by celestial equator? So there is very simple concept. Your Earth is moving around the sun on a path which is called as the ecliptic plane. Okay, that on that plane, Earth is inclined towards its axis by 23.5 degrees. That's why this Earth equator and ecliptic plane form an angle which is 23.5 degree. That equator coincides with the celestial equator. So let's say you have a huge balloon, huge round balloon or a celestial sphere. In between the center of the balloon, you have Earth, which is slightly inclined. When it is inclined, its equator as well as the celestial equator are in the same line. Okay, but the ecliptic is straight, just half of that balloon, or you cut a slice from that balloon, just half, that would be the ecliptic plane. That is the plane of Earth around the sun, but it will have a 23.5 degree angle between the celestial equator or the line or the plane containing Earth's equator too. So this is the two fundamental planes we are talking about. One is celestial equator perpendicular to CEP, then the ecliptic equator, which is the Earth's orbital plane. Okay. Then obviously its pole will be called as NEP, north ecliptic, and vice versa, south ecliptic. Okay. The angle between these two planes are obliquity, which call as 23.5 degree. Inclination of these intersection of these plane is when joined from the Earth center of mass will points towards vernal equinox. Okay, please remember, it is vernal equinox. It is pointed towards vernal equinox. The coordinates of an object on stars can be defined on these two planes. One is either on celestial equator or on the ecliptic plane. So when you define a celestial, use the celestial equator, you see, if you define a point on a star, so this is, let's say this is the star. If you define a point on the celestial equator, so this is, you move on celestial equator like this, you go back and this alpha, and then on perpendicular to this, you will go by delta. So this is called as right ascension alpha angle in the equatorial plane, which is celestial equator, measured counterclockwise. Okay, and from the vernal equinox. The declination angle above or below the equatorial plane. Or if you move on the ecliptic plane, the second plane, this is your second plane. If you move on this plane, it would be ecliptic longitude and ecliptic latitude. So ecliptic longitude would be lambda, latitude would be beta. So for the same point, you have a right ascension and declination, and latitude, ecliptic longitude and latitude, and they would be transformed to each other with the help of this so-called the obliquity, which is rotation of 23.5. So this is one basic example, but again, what is the problem? Problem is whenever you look at such figures, you have too many questions in your mind. Okay, why this NEP? Why this CEP? Why this vernal equinox? What is this vernal equinox? Vernal equinox is also known as first point of Aries. So I mean, we the astronomics, they are using these simple mathematics of this the so-called celestial bodies to define how the movement of the rashis, the sign, zodiac sign, they will change over a period of years. So, but this is the simple convention by which we are explaining. The reality is little different. How this reality is little different, I will tell you. I'll just again stop it here, and I'll share one very nice figure which I've just seen in fact, I've seen it in the last class itself, but for you, I'm sharing it again. This is a very good figure. Okay, I'm just. Are you able to listen the audio also, Sumit?
No, sir, voice is not coming.
Okay, no issues. So I'll just mute it down. I'll just run it. Okay. So this there are two frames we are looking at. The two frames which we are looking at. One is this Eclipse J2000 and this J2000 only. There are two different frames which we are looking at. When I say eclipse, that means it is ecliptic plane we are considering for defining the XYZ. And when I simply say J2000, we are looking at our conceptual old understanding of the equator, which contains the Earth equator. So this is the space in which you are. So I'm just opening the frame again. So your Earth is moving. Okay, you are just you are in space. This is your sun. You are in space. Sun is in the your so-called ecliptic orbit, moving around the sun, but it is slightly tilted. Why you could understand why it is tilted is because this J2000Z, which we are looking at here, this is the axis of Earth. Earth is inclined from its perpendicular Z. It is inclined towards 23.5 degree from that ecliptic plane towards this the right side. So this is your actual Earth rotation axis. This is your Earth rotation axis. It is inclined from this ecliptic plane, the plane which is this. I'm just going. This is your plane. This is your ecliptic plane. So ecliptic normal look like this, as if everything is straight. But when you look at the side view, when it is coming at the side view, this is the side view. The Earth is slightly tilted from Earth, this ecliptic plane, and that's why these are the two different XYZ frame we are looking at. One XYZ is which is nothing but the X, which is mean sorry, this zero longitude line, intersection of Earth equator with zero longitude, then Z containing your Earth rotation axis, and Y perpendicular to make a right-handed coordinate system. Then you have a different XYZ frame. Obviously, the X is same here also because it is the intersection of the ecliptic and equator. So X is same for both. You see here, they are merged. You cannot read anything. It is merged with ecliptic J2000X with the simple J2000X. So XZ is merged, but obviously, since Z is different here, it doesn't contain your Earth rotation axis for ecliptic plane, which is also known as the NEP. This is your NEP line, but the CEP contains this Earth rotation axis. So this is CEP, this is NEP, this is your Earth, this is your X pointing towards vernal equinox, okay, and this is the two different Z. Why two different Z? Because one is perpendicular to NEP and one is perpendicular to CEP. That's how it looks like. Your Earth is moving. These are our other planets represented by a point here only, Uranus, etc. So there are two different frame we are talking about. One is equatorial and ecliptic. So Earth-centered inertial frame we are when we look at the previous figure, this figure, this is the called as the Earth-centered inertial frame. Inertial is a word which is not fit here because you are looking at some body which is moving, but it is a quasi-inertial frame. That means although it is moving, but it looks at as if it is at the rest. Okay, so it is a quasi-inertial frame, we call it in our classical mechanics. This is the quasi-inertial frame. That it is moving by your naked eyes. You are seeing that it is moving, but it look at as it is at the rest. So with this figure, we are also explaining two more things. You see the right hand figure, you just observe your right hand figure like this here. Focus on here. This is how your Earth is taking 26,000 year. That rotation axis, this yellow arrow is taking 20,000 year to come back to again the same position. This process is called as precession. This precession is secular precession. It will take around 26,000 years to come back again at the same point. So initially it was pointing to Alpha Draconis, then Polaris, then come to Vega, and then again Alpha Draconis. So to point that again Alpha Draconis, this has to go through the 26,000 years again, then it will come back here again. Okay, on in here you have the sun at the center, you have Earth, you have Moon, you have Mercury, other planets. They are all similar to ecliptic. Well, I mean, every planet have that same ecliptic plane for its orbit around the sun, but they are at the same level. It's not like that the level is different. Only is the size of the orbit is different, except this Pluto. So this your Earth rotation axis, you look at it, see here it is shown in a sense that you should understand the body which you consider as inertial has a very positive sense towards its moving its rotation axis. That animation is little fast, but see, because the period is very huge, 26,000 years. So that's why this motion is, we are representing it here as very fast, but in fact it is slow. This is your latitude line, white line. This is your latitude line, which is 0 in Earth-centered, Earth-fixed frame. Okay. So you just open your, this finger, index finger, and you rotate your hand in this similar fashion. So that's how this Earth wobble in the space. Okay, again, this is your Earth-centered, Earth-fixed frame, which you are looking in this space. When I say Earth-centered, Earth-fixed, you see the Earth is not moving. This is your Earth-centered, Earth-fixed. See, the Earth is not moving. We introduce this one frame, which is, we call it the Earth-centered inertial frame. The moment we introduce, you understand that the two Z are merged. Please remember, here we are not talking about the NEP anymore, or the we are not talking about the ecliptic plane anymore. Here we are representing simply the two frames. One is Earth-centered fixed and Earth-centered inertial. In both two cases, the so-called X would be different. The X is different in a sense that your X in the Earth-centered fixed frame is representing the intersection of 0 meridian with equator. But in the Earth-centered inertial, it is the intersection of the equatorial plane with the ecliptic plane. Okay, the plane of Earth's orbit around the sun. So both X would be different. One is obviously the again I'm repeating, in the Earth center, this figure represents the Earth-centered inertial and Earth-centered, Earth-fixed in a same Earth, and Earth-centered inertial has x-axis. I'm again repeating, Earth-centered inertial or space-fixed has x-axis, that is intersection of ecliptic with equator and line joining from Earth center of mass to that intersection point. But in the case which is this x, which is this x, this is at different x, IAU, which is International Association of International Astronomical Association, International Union of I think astronomic. So this X is so-called intersection of the so-called ecliptic and equator, and this X which is hidden behind this Earth is the Earth-centered, Earth-fixed X, which is intersection of zero longitude line with equator. Okay. Obviously, Z is the same for both. It contain the Earth rotation X, but there is a slight difference. It will come when we'll run the animation. It will be little different. Let's see. We are running the animation. So this is your. See, the movement will only take place in the Earth-centered inertial. The Earth-centered, Earth-fixed will remain fixed at the same place. So you will not see the change in this X. You will only see the change in IAU Earth X, which is Earth-centered inertial X. And now you will see the little deviation in the Z axis also. You see that now two arrows are coming out of the same place. These two arrows are coming. Initially it was only one. You see, here it is only one arrow. There is no other arrow you are observing, as if both coincided at the same point. But the moment some time lapse has happened, some 2,500 years are of revolution has taken place. You see, there is a shift in this two y z axis. I'm sorry. That two z axis are nothing but The 2z which is coming out of it is just because your Earth has taken a leap of 2500 years of rotation. So obviously the z will not be same as the z of the Earth-centered earthquakes. Here the z has shifted because it has to cover the 26,000 year of rotation. It will again come back to the same z when it will be 26,000 year. I hope you understand this part. This Z2000, which is located for defining the inertial frame, it is Earth mean equator 2000 frame. Definition is based on the Earth equator and equinox and determined from observation of planetary motions plus some other data which is obviously there. So you see here Z is normal to mean equator of date of epoch Z2000, which is the approximately Earth spin axis orientation at that epoch, and this epoch is nothing but 1 Jan 2000. Okay, this ecliptic plane defined by movement of Earth around Sun, equatorial plane normal to the Earth spin axis Z. So these are the two frames. One is blue, one is this black. The intersection of ecliptic to equator is the x of the intersection of equatorial and ecliptic plane called vernal equinox. This z, this z is obviously orthogonal to this z. So this is the inertial frame we are talking about. Okay, this is the inertial frame we are talking about. The equatorial plane, which is plane normal to Earth, is spin axis z. Okay. So this is at epoch, at a particular epoch, you are defining the XYZ for an inertial frame. Okay. There is one more figure which would be of your interest. Just please wait. This video is available. You just simply write the title, which is written here, Earth-centered inertial frame definition. You can simply go look at this video from your YouTube also. Last year I got this video, so I've shown it to your previous batch also. It's very good figure, because sometimes the understanding doesn't come from your realization. You just have to visualize it for also. So we are introducing the space frame as ecliptic and the Earth fixed. So again, the same frame. The one is ecliptic and another is the Earth-centered inertial frame. So you see your ecliptic plane or on the Earth equator. Sorry, your Earth-centered inertial frame or on the equator, and the ecliptic one are having some deviation. Ecliptic one are having some deviation. This is the ecliptic line. Just for your understanding, just see how the two frames are selected. So how do, if one is ecliptic, another is inertial. So I hope this little understanding the rotation axis and etc. would be much more clear by visualization. So whenever I ask you to go back in space fixed frame or Earth inertial frame, you go back into the space, and what you are looking at? You are looking at your Earth, which is moving very slowly. It is moving. Okay, so when I say it is moving, that means obviously we are talking about the Earth rotation vector, isn't it? So the rotation vector is defined as omega e. So the vector is always defined by its magnitude as well as its unit direction. So the omega e is represented by omega hat and multiplied by its magnitude. So omega e oscillates. Oscillates. Why? I have told you, na. It is this your so-called motion of the z-axis is taking 26,000 years kind of line. So WE oscillates because of gravitational torque exerted by the moon, sun, and planets. Displacement of matter in different parts of the planet itself, including fluid, envelopes, and other excitation mechanism. So this WE oscillates because of the forces acting over the Earth. This oscillation of Earth rotation vector is oscillation of the unit vector omega, which is with respect to the inertial space because of the lunisolar tides. We call it precession, and short periodic nutation. So this 26,000 year of this so-called the oscillation is having a short periodic nutation also, where a short zerk is introduced in this Earth rotation axis. Just visualize your you have you know a ring of what should I say? How do you define it? You have a ring in your hand which is tied from multiple points. Now this ring is tied. The upper ring of that Earth rotation axis, the side figure which I was showing you, it is rotating in 26,000 years up. It is coming again back to Alpha Draconis. So this upper ring, let's say visualize the upper ring, it is tied at those 4 points, Alpha Draconis, Vega, Polaris, these are tied. And in between Vega and Alpha Draconis, you put your finger and exert some pressure. So what you will see? You will see a vibration in the ring, isn't it? That vibration is short periodic because it will not last forever. It will be short periodic, and it is of 18.6 years. Annual period of such exertion is 18.6 years. They are called as nutation. So with respect to inertial tides, with respect to inertial space, because of lunisolar tides, we have precession and nutation. And with respect to Earth crust, see, the effect of gravitational forces is there, but in inner fluid changes as well as the mass shift also occur, and that will shift the Earth rotation axis. That is called as the polar motion. So oscillation of the norm, variation of speed of rotation, this will create variation in the time. So one is the vector change, another is norm or the magnitude of the change. So see here, this is the vector, this is the unit vector. If it is change, it is precession and nutation and polar motion. If this change, it will create the delay in time. So you see, if your Earth moves faster, the day will be shorter. If Earth moves slower, the day will be longer. So that means time system would have certain effect over it. That's why the two different, one is oscillation of the unit vector omega and oscillation of the norm. Just please have a look at this side. Just try to grab the concept. It's very simple concept. You have Earth rotation vector omega e, which is represented by unit vector omega and multiplied by the magnitude of it. Okay. Thus this omega e oscillates because of gravitational torque exerted by the moon, sun, and planets. This displacement of matter in different parts of the planet and other excitation mechanism. The oscillation of Earth rotation vector, which is oscillation of unit vector omega with respect to inertial space because of lunisolar tides, precession, and nutation with respect to Earth's crust, polar motion, and oscillation of norm or magnitude. I mean, the speed with which they are moving, if it is changed, it will affect the time. Any questions or any doubt? Okay, if there is no question, we can move ahead. So this is very beautiful figure of precession and nutation. So in 2000 BC, it was pointed to Alpha Draconis, and now it is to Ursa Minor, now pointing to Ursa Minor. And you see the nutation, short periodic nutation, as if some external extra force has acted over it. So because of lunisolar tides, the Earth rotation axis oscillates with respect to inertial space. That these oscillation you can only feel when you are outside the Earth. You are in the space and you are visualizing the rotation. Okay, and in imaginary rotation axis coming out of the North Pole. Okay, so this oscillation is partitioned into secular precession, that is sun attraction on Earth equator bulge, which is not in the ecliptic plane, the torque that tends to bring the equator in the ecliptic plane. Okay, as if you are just looking at this torque, you say the sun and moon is acting over the rotation of this see, Earth is rotating around the sun. Okay, and it is slightly tilted away from the ecliptic plane. So what sun is doing, sun is saying, why you are uh, you know inclined away from me, you just come in my plane. So it tends to apply a torque that forces the Earth to come in the plane of ecliptic. But when it happens, Earth also exert the same torque but in opposite direction to remain in that plane of its own. That resultant force creates these the so-called nutations. I mean, the short periodic until it passes. This is it creates certain vibration in the rotation axis. So secular precession, sun or moon attraction on Earth equatorial bulge, which is not in the ecliptic plane. Torque that tends. अब आप यहाँ पर ये भी देख लीजिए कि Earth का moon का भी orbit चल रहा है Earth के around. So that is also additive forces that is acting. That's why we are including sun and moon both. Attraction on Earth equatorial bulge, which is not in the ecliptic plane. So torque that tends to bring the equator in the ecliptic plane, opposed by centrifugal force of due to Earth rotation. Okay, that periodic nutation, which is main period is of 18.6 years. So sun and moon passes equatorial plane, tidal torque 0, creates semi-annual and semi-monthly periods. There are semi-annual and semi-monthly irregularities as well, result in small oscillation, also called forced nutation, superimposed on secular precession. So these are semi-annual and semi-monthly also sometimes irregularities because of the passing of equatorial bulge and these forces acting over it. So this figure is very good figure. Obviously, this figure can only be visualized from inertial space, from away from Earth. That's why the first line itself says, you see here, this says, because of lunisolar tides, the Earth rotation axis oscillates or seem to be oscillates with respect to inertial space, with respect to stars. Okay. This is the NEP, the ecliptic. See, the ecliptic plane has no value in our coordinate system. We are mainly attracted to two coordinate system. One is ECI, which is Earth centered inertial. That means this system, which where you are looking at your Earth rotation axis and your Earth. And another is, I mean, this system. When I say what coordinate system, that means I'm talking about this system. This is the system which we are interested in. We are not interested in any kind of NEP system. We are simply interested in this celestial equator CEP system, Earth-centered inertial system, and Earth-centered Earth fixed, because that's where we want our coordinate on the surface of Earth. So that's how the precession and nutation will take shape. From an accurate treatment of precession and nutation, one must account for precise lunar and solar orbital parameters, use of astronomical tables. In addition, any process that modifies the Earth movement of inertia will induce variation of its rotation vector. Recall that angular momentum L is equal to I inertia multiplied by your omega, and must be conserved. For instance, solid Earth tides, oceanic tide effects, which is tidal plus non-tidal, atmospheric effects, pressure distribution around the Earth's surface, and free core nutation, rotation axis of core and mantle not aligned, that will also create 432-day period nutation. That means, please remember, it is not only the final external forces that create nutation. This last line says that your core and mantle, which is the constituents of your Earth, if it is not aligned, that will also create the few free core nutation, that is of 432 days. So you see here, dPCI is the secular precession, and d epsilon is the representation of precession and nutation, the offset in the latitude and longitude. So offset in longitude, dPCI, and in oblique dEps of celestial pole with respect to old precession nutation model, which was developed by International Astronomical Union in 1980. You see the deviation from 0, it is deviated, and in 2004 it is having minus 50 dPCI. And similarly to d epsilon, variation or oscillation was occurred, and it was observed that it is now at, in 2004 somewhere around it, or maybe 2000, near to 2005 6 2006, it is somewhere around -2 MAS, milli-arc second. Okay, a 1 arc second is of 30 meter at the surface of Earth. 1 milli-arc second is of 3 centimeters. So the offset is of somewhere 6 centimeter in the case of obliquity, and somewhere around 150 centimeter the shift in the longitude. Okay, you can read it. The graph reading is very simple. You must have done during your JEE preparation. The graph reading is very simple. These are the years These are the variation in the milli-arc second from the same point which was shifted, then this occurrence, then again come back to its old position. Because this is the periodic cycle which we are observing, isn't it? So the longitude in represented in d5, which is longitude of a particular position, and in obliquity also, which is epsilon, the angle between ecliptic and equator. Okay, so any questions so far? So this another concept is called as Chandler Wobble. Please remember in your Earth rotation vector slide, this was the slide. We have discussed this, isn't it? We have discussed the oscillation of unit vector with respect to inertial space. That means precession and nutation. But we have to study the with respect to Earth crust also. What happens to Earth unit vector with respect to Earth crust? So we have studied precession and nutation. We have seen it, the movement. This is the movement precession nutation. This is the Chandler wobble. So if rotation axis of rotating solid does not coincide with the polar motion axis of inertia, for the angular momentum to remain constant, assuming no external forcing, the angular velocity vector has to change. Okay. So I'm again repeating if rotation axis of a rotating solid, if rotation axis of rotating solid does not coincide with polar major axis of inertia, for angular momentum to remain constant, assuming no external forces acting over it, the angular velocity vector has to change. True for any irregularly shaped rotating solid body like Earth, happens in the absence of external forcing called as free wobble or free nutation. So that's the concept. Okay. On Earth, free wobble is called as Chandler wobble in honor of S.C. Chandler, who first observed it in 1891. With respect to Earth's surface, position of instantaneous rotation pole moves around polar major axis of inertia. So this Z is not at the same place. In fact, it is moving. It is having a period and it is moving. I'll show you one figure in the next slide that will shows how it moves with respect to Earth's surface position of instantaneous rotation pole. Please remember from your basic physics, you can correlate with many of the topics. Instantaneous means at any time t is equal to t1. This is the instantaneous. The rotation means rotation pole means the z-axis which we are talking about around polar major axis of inertia. This is the inertia for if the body is to remain in the angular momentum, the angular momentum to remain constant, the rotation has to be there with respect to this, but it is not the actual case. It is moving because of the wobble, it is moving around that particular axis. And the theory gives this 305 days, and observation says this is the 430 days of the Chandler wobble. This is the free motion, free wobble. There is no external force acting over it. It constitutes its own because of the inside mechanism, because of the mass shifting, because of the fluid displacement, because of the flux displacement inside that Earth. This free Chandler wobble is there of that is of 430 days. That means the axis, the instantaneous z axis will not be at the same place every time. It will have a 430 days kind of period and it will again go back to same position after 430 days, isn't it? That should be the Chandler wobble. That is the free wobble. This is the polar motion. But when you know that it is a free wobble, but your Earth is not a body where everything is constant. Every time sun is attracting gravitational attraction, moon gravitational attraction is there because of the tides you are having. The attraction are so huge that you have tides in the ocean. The attraction you can understand this such kind of attraction you are having. So observed Chandler Wobble, which is period of 430 days, which is amplitude of 0.7 arc second, that is of around 15 meter on the Earth's surface. Difference between observed and theoretical values. A mystery for a while as astronomers were search for a 0305 period without finding it. Due to non-perfect elasticity of Earth, some energy is transferred into an elastic deformation, damping of Chandler Wobble. So calculation using the inelasticity of Earth shows that Chandler Wobble should rapidly damp to zero in less than 100 years. There must be an excitation mechanism that keeps it going. That means people were saying that it should be uh, zero within 100 years, but there must be some excitation mechanism not understood till recently. Two-thirds of Chandler Wobble is caused by ocean bottom pressure changes, the remaining one-third by fluctuation in atmospheric pressure. Please remember, this is the very good point, which I mean, you should know that the Chandler Wobble is not damped to zero. Why? Because of the two-thirds of the Chandler Wobble is caused by the ocean bottom pressure changes, the remaining one-third by fluctuation in atmospheric pressure. So these are the two pressure mechanisms that are affecting your uh, so-called Chandler Wobble. The polar motion actually has three major components. One is Chandler Wobble. Second is annual oscillation forced by seasonal displacement of air and water masses, nearly about 2 meters. Diurnal and semi-diurnal variation forced by oceanic tides, which is about 0.5 meters. So these are very good figure which is representing you. So in 1891, till the Chandler has observed these motion, see, it is coming here, 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 here. Then it is coming here. In 1970, I think in 1950, just to this 1970, there was nothing like any periodic motion. This is a very strange point. But from 1970, it goes into till 2000, or maybe in before 2000. There is some polar motion for the period of 1996 2000, which is a dotted line, and polar wander since 1819 axis in arc second. So this continuous line is a polar wander. So when this picture was prepared in 2000, it was marked up to here. This is the polar wander. That means this axis has no idea what is happening to it. It is just moving. And this polar motion, this is the Chandler wobble we are observing. But this periodic motion, the dotted line, which is polar motion, we are for the period of 1996 to 200, it has a continuous change, and it is a periodic in nature. Sometimes it will again go back and come back here again. So in 1996 it was here, this 1907, this 1908, 99, and to then anti-clockwise it is coming from outside circle to inside circle. Obviously it should have been here. Ideally, if the case, this should have been here, but it is shifted, this xp and yp, which is called as polar motion. So non-auxiliary motion with respect to Earth crust, which is polar wander, that is of 3.7 milliarc second per year towards Groenland. So there is position on Earth surface, Groenland. You can search where the Groenland land is. So the x-axis is coming out on. Let me just see. Where I have also not seen where this Groenland is there. Land. Yeah. Any guesses where it should be? That will check your concentration to the content. Anyone? कहाँ होना चाहिए ये?
Sir, this must be towards the pole.
Yes, nearest to the pole. Yes, it is near in somewhere in Norway. It's highlighting. So this Groenland is somewhere near uh, Norway right now. Shifted from North Pole. This was supposed to be position, but it shifted. So that's true because of the polar motion we are getting. So how this value is given to us? This value is given to us by some XP and YP. Okay. So I think you have got enough content for today. This is a new content, but it's very interesting. I mean, I have read it somewhere uh, in 2016-17 about this polar motion. A lot more content. Then I introduced this concept to this class. Previously, I was not explaining this, but it's very much interesting. If you know basic physics, basic understanding of angular momentum, tidal attraction forces, then you see this concepts very much popular. And in 18, when Thomas Herring came here in Allahabad to deliver gamut lectures, and he also explained a lot about this. Okay. Anyways, any questions? I'll share the slide, two slides today with you.